Hello, everyone. Thank you for joining. My name is Ankit Jhalaria. It's very nice to meet you all. And I'm here to talk about Godaddy's journey into building a streaming data platform and running pipelines on it from the ground up. Um, so most of you are probably already familiar about what GoDaddy does. So we are the place where entrepreneurs would come, start, grow, and successfully run their online presence. And we are proud to do this for over 19 million plus entrepreneurs who in turn then help their customers. And in order to help our entrepreneurs, we help them with a variety of products. And I've listed four of them on the left. You could buy a domain name with GoDaddy. You could set up your website with GoDaddy. You could buy search. You could set up. You could use our templates to automatically set up websites and things like that. And now, when you're operating at this scale, you really need to make sure your data, the data that you're collecting, can help your customers at the end. So, with that in mind, I wanted to start with why do we need a streaming data platform to begin with? And before I get to an answer for this question, I wanted to talk you guys through a use case. So let's say you are a potential customer. You go to GoDaddy.com and you're trying to set up a new venture or a new company, and the first thing you do is you buy a domain. You search for startdataplatform.com and you see that domain name is available. So you go ahead and buy it for $1. Now, once you buy a domain, you realize I also need to set up a website. I also need to get SSL certificates. Now, how do I do that? So there are a ton of offerings that we do, and you as a customer could benefit by talking to our amazing care team. We call them our care agents, and their goal is to help our customers or our entrepreneurs with the best set of products that can help them. Now, if you think about it, if you had a batch system, uh, for them to know about what to know that you just made a purchase, it would historically would have taken like 24 hours if you're running a batch processing every day, or a latency that would not be close to real time, or it would not be low latency at all. So now when you have a streaming first approach, or when you build a streaming platform, you help your customers with that data right away. In this case, our customers being our own care agents who can then help our customers. So this was one of the primary motivations for us to invest in building a streaming data platform. Now, before I delve into our platform architecture, I wanted to briefly talk about a couple of architectural patterns that folks might already be familiar with. On the left is called the Lambda architectural pattern. It has been used for over a decade. It consists of essentially having two distributed systems. One is your batch system, and one is a low latency streaming system. The batch system will eventually have all the data corrected when it is run, and low latency, your low latency distributed system will get you like approximate results, and then you unify them with the batch layer once it's done, and then you have an API layer on top of it that knows how to combine the batch data and the streaming data, and that's what your end users use for queries. The pattern on the right, however, it's called the kappa pattern. It might look similar to the pattern on the left, minus the batch layer. So in a kappa pattern, there is no batch component. It's designed with keeping in mind streaming first as the principle, and then it is flexible enough to allow you to run your batch jobs if you have to. But the whole concept of and the benefit that you get out of Flink is it's also designed with keeping streaming in first, and then batch is just adding a bounce to your stream of data. So if you have an infinite stream, and if you add a start and an endpoint to it, that's essentially your batch. With that said, let's look at our architecture, or GoDaddy's architecture. So this is a very simplified version of our architecture, and I've divided this into three different components. On the left is the ingress layer. So this is where your sources of data are, or your producers of the data. So if you made a purchase on GoDaddy, the data would go in some database. It could be MySQL, it could be SQL Server, and then we have a change data capture enabled on SQL Server so that we get those stream of events sent into some streaming fashion. We also consume data from API sources. So this ingress layer on the left is how you get the data in the first place into the platform. We use Amazon's Kinesis to have those stream of events written to Kinesis. Think of Kinesis, if you're familiar with Kafka, it's essentially a stream where you can write your changes. We have enabled and Kinesis has a retention of 7 days. After that, the data is dropped from that stream. So in order to still have that data available for future querying, we write that data to S3 via Firehose, and S3 in this case acts as our persistent storage or cold storage. So up until this point, the data, this was talking about the sources of the data. Now it gets into our platform. There are a couple of ways you could write your jobs in Flink. You could program directly against the Flink APIs, or in our case, we decided to use an abstraction language called as Apache Beam. And we write our language in, we write our program in Beam, which runs on Flink. And I'll go over why we went that route. So essentially, at the end of the day, we are running our platform on Flink. And essentially, if you're thinking about writing a streaming pipeline, you may be looking at doing some aggregations, and that's what your transformations or your business logic would be. And in our case, you define that in Beam. Once you do that, you eventually output that data somewhere. It could be to a database. In our case, it's RDS running on Amazon, or it could be sending notifications via SNS. And one use case that we have is once you make a purchase, we want to send you a receipt of the purchase that you made. And this writing the events out to SNS helps our marketing team to trigger those events in almost in a real-time fashion. And then we have our APIs built on top of these output sources, so that our care team, as one example, can use those APIs. And when you make a call now to our care teams, they have that data about a recent purchase that you made almost right away, so that they can better assist you. And then on the right is a set of standard reporting tools that a lot of the marketing teams or the analytics folks use, including Athena, Tableau, and Redshift, that rely on the data produced by our pipelines written in Beam and running on Flink. And then on top of all of this, we have monitoring/alerts across each component that tell us if something went wrong in a certain system, what system was that, and we can take actions right away to essentially fix it. So before I dive into our actual pipeline code and what does that look like, I wanted to talk about what does it mean to do joins in a streaming world. Folks are almost familiar with what does it mean to do it in a batch. It's pretty intuitive. If you have 3 data sets, in this case, customer, domains, and bills, you could write a MapReduce job, you could write a pick job or a Spark job that takes this data and produces a point-in-time snapshot, because these data sets by definition are finite, and you know how to write jobs to process them. In the case of streaming, however, streams by definition are infinite. They never end. So in my example on the bottom, let's say you have 3 streams, each having information about the first one has information about the customers, the second domains and bills. Now, what does it mean to join these streams together, and how do you even join something that's infinite? That's where Flink has this notion of having a window and a trigger. So if you're trying to say, I'm going to aggregate the events that I'm getting from these different streams, you define a window. An example would be a fixed window, let's say, of a minute. You're saying, I'm going to collect all the events that are happening across these streams for that 1 minute. I'm going to run my transformation or business logic that defines what does it mean to compute that aggregate. And then I'm going to emit that record downstream to be written in the database so that I can present that via APIs to a dashboard that is potentially tracking a key performance metric for how your business is running. So the notion of windows and triggers and the late events comes in really handy with and that's how we use essentially Flink and all the state about. So let's say you have a window of a minute, and 2 of the streams they arrive on time while the third doesn't. So you can still store that state in Flink and update it later when the third event arrives, so that you're not losing on any data. And that's how we essentially use stateful processing with Flink. So now I'm going to go back and forth between this slide and the next one. So essentially, one key component that one should keep in mind when writing a data platform is to make sure that you have the right set of abstractions for your customers, or in this case, your platform or pipeline authors, to make it easier for them to onboard. So we are leveraging Apache Beam as that abstraction language, and we have built SDKs on top of it. So as one example of that SDK is, as a pipeline author, like if you look at these 5 or 6 lines of code, you define a pipeline, and in this case, you're saying, I'm going to consume the data from a Hive table. all you are doing is you're saying, here's the Hive table abstraction that we built on the platform. I want to now read data from this protobuf message, which is in this case is saying it's reading the data from a domain search snapshot table in a domains database. And the end result of this is one line of code, and you get that data read into an infinite collection, or like Beam likes to call it a P collection. Now you take that data, you apply a transformation, you could massage the data, you could add an aggregate or do whatever, and you write that transform, and then eventually we have this sync, which takes that data and writes it into a database. You could write it to HDFS, you could write it to S3 or any configured target. So the abstraction that we provide then for pipeline authors is essentially the first thing on the left. You define what your input sources are, and you define that via protobuf messages, and we already have done the work for the most of the sources. So once you know what source you're consuming, you write a transformation, and this is where the pipeline authors add most value, because they know what the business logic is, and they write the transformations inside Beam. And then once they're done with the transformations, they define what a window is, how long they want to accumulate the results, and when to fire an event downstream. And they define a window and a triggering condition, and that's how the data goes downstream into a sink, essentially. And this, again, by sink I mean various egress sources. It could be writing to a database, writing to a file system, writing to a notification service, or whatever that egress is. So another example is as a business tracking metric, we try to find out how many times people are searching domain names on GoDaddy per second. So as an example, if you're trying to build a pipeline that is doing this aggregation on the fly, you would define, let's say, an input message that says, here's my table, here's my input source. In this example, it's a Hive source. It could be a Kinesis source. And then you define an aggregate proto, which is saying, I want to do an aggregate based on device, on where the actual search happened. And then I'm going to emit a searches per second metric every second. So now, when you're thinking in terms of actual code, what would that look like if you were to do this on our pipeline? You would define essentially like the following lines of code will help you do that. So essentially what that's saying is, I'm going to define a fixed window of 1 second on Flink. I'm going to accumulate those events for that 1 second, and I'm going to allow a lateness of 1 second, and this lateness is what you would know about your pipeline and your data. In our case, we're saying we'll allow late events up to 1 second, and after this has happened, we're going to run a combine operation based on a key. In this example, the key would be the device on which the event happened. Once you do a combine operation on Flink, you are going to get an output in which you're saying, here's how many number of searches are happening per second. Then that acts as a business metric for us to keep track of how many domain searches are happening per second, as an example, to figure out what that health of the system is. And this is just one example. We do a ton of other things with these pipelines to get us those business metrics. And then this combiner is just saying, this is a simple binary combine function that's saying, take what's on the left and what's on the right, and you add those together. And this is a very simple example of counting the number of searches that are happening per second. And the end result of this is an aggregate which will have a count based on the device and gets emitted every second. So now, one other important aspect that we learned in our journey over the past 2 years of building pipelines, if you have to onboard building a platform is one thing, but then getting that wide adoption across the company, you have to make it easy for your pipeline authors to quickly grok the new framework that you've built, but at the same time, make it easy for them to write these pipelines. So that's where our platform abstraction came in really handy. Us investing time in building these sources and these syncs on top of Apache Beam helped us to set that groundwork and made it very easy for folks to write pipelines. One other thing we achieved with by following this approach was that we run our pipelines on AWS, on Flink, in Kubernetes. And that said, we run the exact same pipeline code on Spark on our own clusters. We run a streaming version of the pipeline with the same code. We run a batch version of the pipeline with the same code on Flink and on Spark. So keeping this thing in mind, that that you have to future-proof your pipelines. And one example that I have for this use case was when we initially started building this framework, we started writing our code in Beam, but we were deploying it on Google Dataflow. And then 6 months later, we switched it to a different cloud provider, Amazon in this case. We had to make really minimal changes, and we were able to do this switch with almost no dev effort. And I say almost because it still took a week to do that transition. But if you think about it, we didn't have to write anything from scratch again. We could leverage the same pipeline code that we wrote, and now we can deploy it on AWS with Flink running on Kubernetes. So now, what does a deployment lifecycle look like for us when we are deploying our pipelines? You write your pipelines using this abstraction language of Beam and our own SDKs. We build a Docker image with an Uber jar, which is all the dependencies. We spin up a Flink cluster on Kubernetes. We have a Flink cluster per pipeline that we are deploying. So every pipeline that gets deployed gets its own Flink cluster. Now, smaller pipelines will have one job manager and probably a few task managers, whereas the bigger pipelines would have a job manager and tens or hundreds of task managers with high availability enabled. So once you do that, once you submit a job to your Kubernetes cluster, we do this thing called as node rotation, and that is a requirement to when you have these Kubernetes pods, you want to still do node rotation, meaning if you have a security patch, you want to remove those nodes and get a new one. You could do that with Flink's save points. So you take a save point of a running pipeline. When you restore it, you can restore from that save point instead of processing all the data over and over again. And then we follow a blue-green deployment-based approach, and that essentially means if we have a running cluster already, let's call it the blue cluster. If you are deploying a new set of pipeline changes, we'll spin up a new cluster. Let's call it the green cluster. We'll have that cluster catch up to the current events that we are processing, and we'll do a validation on that green cluster to make sure everything looks good. Once it does, that's when we'll do just a DNS switch, and then you're onto the new cluster. If things go wrong, rollback is pretty easy as well. All you have to do is just change your DNS again to point to the older one, and you have almost close to zero downtime. So this is how we are leveraging Flink. We also have enabled incremental checkpoints to have periodic checkpoints while we are running these pipelines. Let's see. Oh, so I think one of the key learnings, or a few of the key learnings that we learned during this exercise, was having the right set of abstraction is fundamentally very important to have a wider adoption of your platform. And I could not stress this enough. And I think we did probably a reasonable job with that. And then using a state backend, in our case, we use Flink with RocksDB to store the state. If you remember in one of the previous diagrams I was showing, we're consuming data from a few streams. Joining them, let's say you have 3 streams and you join 2 streams, and you have to store that data somewhere before the third stream gets its event. In our case, we do this with tens, in some cases hundreds of streams at the same time. So using a persistent storage or having some way to store that state is really important as well, and we use RocksDB for that. And then with Flink, the beauty with Flink is it provides a natural way. It's designed with keeping in mind streaming first. However, running batch is also pretty easy with Flink. So that's when it seemed like a natural fit for us to use Flink. And we use our same pipeline code, again, as I said in the beginning, on our own clusters as well. And this is to support some of our legacy use cases. We run the exact same Beam pipeline code with our core platform SDKs and run it on Spark on our own clusters, and the same exact code on Kubernetes, on Flink in AWS. So anybody who comes on board onto our data platform team, we recommend them at least reading the streaming systems book available on Safari, and I've listed out a few sources for learning more about the Kappa pattern, the Lambda pattern, and Flink, and links to Flink and Beam. So if you guys have not read streaming systems, I would highly recommend that book. And that's it. Thank you.